Welcome to SafeHPower. SafeHPower aims the continuous monitoring for the safe storage, distribution and usage of hydrogen power for transport. It is an EC-funded FP7 project coordinated by Flotex. This presentation provides a general overview of the Neutron Radiography system that has been developed for total imaging and precise location of fatigue cracks and embrittlement sites in hydrogen storage tanks. The information on tank samples and different experiments are presented on color-coordinated slides for the viewer's benefit. This video presentation will address the following aspects related to the Neutron Radiography inspection system, techniques and the technology developed under the SafeHPower project. This comprises of an introduction to neutron radiography, advantages of neutron over X-ray radiography, overview of the tangential neutron radiography system, setup and working of a fast neutron radiography system using a pulsed deuterium-tritium neutron generator, thermal neutron radiography using a proton accelerator-based neutron source, setup and working of a thermal neutron radiography system using a continuous deuterium-tritium neutron generator, and conclusions. Under the SafeHPower project, the neutron radiography technique has been investigated to conduct total imaging of defects on hydrogen storage tanks. Neutron radiography is largely confined to research establishments and large centralized facilities because of shielding requirements, expense, and a need for intense or high-flux neutron generators. However, in recent years, portable neutron sources with sufficient neutron activity are commercially available. These sources are based on a deuterium-tritium fusion reaction which can produce up to 10 raised to 10 neutrons per second at 14 megaelectron volts. Neutrons can be generated using different processes and are classified based on their energies as shown in the table. Neutrons in the energy ranging from 0.005 to 0.5 electron volt show large differences in attenuation. It is these large attenuation differences that make neutron radiography very useful. So what is the difference between neutrons and X-rays? The mass attenuation coefficient of X-rays of a given energy increases with increase in atomic number as shown by the solid line on the graph. Neutrons, on the other hand, have the reverse qualities. They are neutral particles that interact with the nucleus by either scattering or absorption. The probability of a scattering or an absorption event is expressed through the concept of cross-section in bands. There is a probability for each of these events, and the amount of scattering or absorption of neutrons by atomic number varies in a random fashion throughout the periodic table as can be seen on the graph. What is the advantage of using neutron radiography? Hydrogen has a very large scattering cross-section which provides a good contrast in the presence of heavy atoms such as lead. This makes it possible to detect materials such as rubber and plastics. Conversely, dense materials such as lead, tungsten or uranium are relatively easy to penetrate by neutrons. This sensitivity to hydrocarbons makes neutron radiography a very attractive technology which can be extensively explored for imaging cracks and other defects on a variety of materials including metals and composites. Two types of hydrogen tanks will be inspected using neutron radiography. The first type is a type 1 tank made of steel. Steel tanks are commonly used for hydrogen storage at production plants, for transportation purposes, and at gas filling stations where weight is not an issue. Steel has a hydrogen diffusion rate which is 3 times lower than a composite material and is cheaper than aluminium. A 50-liter steel tank, as shown on the left, was sectioned and a defect 0.5 mm wide and 50 mm long was manually created for inspection purposes. The second type is a Type 4 tank, which is a composite wound cylinder with an inner liner made of polypropylene. Composite tanks are used as hydrogen fuel storage tanks in vehicles due to its light weight in comparison to steel. The tank shown in the left image has been sectioned in half, and the defects, which are 1 and 2 mm wide and 25 mm long, have been manually created on the inside of the wound composite cylinder. In principle, a neutron source, a collimator, a jig to hold the sample, and an imaging device are needed to conduct neutron radiography as shown in the cartoon. However, in practice, it essentially requires an optimum neutron energy, a high flux, a bespoke collimator, and a suitable scintillator to obtain a high-resolution image. A tangential neutron radiography system using a portable deuterium-tritium neutron generator was proposed under this project. What is tangential neutron radiography? Hydrogen has a high scattering coefficient which would make it difficult to detect it within a defect if a tank full of hydrogen is imaged. The background scatter of neutrons will contribute to high noise and fog the image of the tank wall. By focusing the neutron beam on the hydrogen tank wall interface, that is, tangentially, the scatter from bulk hydrogen is reduced and a well-collimated beam of neutrons can be made to traverse a long path in steel, thereby reducing the ratio of scattered to direct radiation and effectively detecting the defects within. The next few slides will introduce the various components that make up a neutron radiography system. The image at the top right is the sealed DT tube, which is the source of neutrons. The bottom right image shows the hardware needed to operate the source. The graphical user interface allows the operation of the neutron source from the safety of a control room outside the shielded facility. This device generates neutrons with an energy of 14 MeV and an intensity of 10⁻⁹ neutrons per second. It is important to mention that 3 different DT generators housed at 3 different sites have been used for experimentation purposes within this project. A bespoke divergent collimator, as shown, was designed and developed to collimate neutrons. As neutrons are emitted isotropically from a DT source, a collimator is needed to focus a beam of neutrons towards the object. The most common collimator design is a divergent collimator. Consortium partner Ceratec conducted Monte Carlo simulations to design a divergent collimator with suitable materials that provides a reduced loss in neutron kinetic energy during collisions inside the collimator, prevent stray neutrons from outside, and any gammas from entering the collimated beam. The neutrons coming out of the collimator encounter the object to be imaged, and after passing through the object must then be detected to produce a radiograph. To this purpose, a detection system comprising of a suitable scintillator, optical component, and a charge-coupled device camera, also known as CCD, was developed in a L-shaped life-proof casing. The L-shaped design ensures that the camera is not placed in direct sight of neutrons and stops it damaging the camera electronics. A scintillator is used to convert neutrons to visible light, and this light is focused on a CCD camera using optical components. A plastic or organic scintillator is extensively used for neutron radiographic detection. Different types of scintillators have been used for fast and thermal neutron radiography experiments conducted under this project. To achieve radiographic imaging, an ultra low light level camera is used to image the scintillating screen. a Hamamatsu electron multiplying CCD camera with excellent quantum efficiency and an ability to operate at low illumination levels has been used for imaging in our experiment. Two types of neutron radiography techniques employing fast and thermal neutrons have been investigated within this project. Fast neutron radiography was experimented using a pulsed DT neutron source housed at the University of Sheffield. Due to physical size of the bunker, a vertical jig was installed using a catenary system as seen in this image. The fast neutron radiography setup comprised of a pulsed neutron source capable of generating 10⁶ neutrons per second at a maximum frequency of 30 Hz. A collimator, which cannot be seen in this image as it is surrounded by polyethylene blocks, a BC400 scintillator, which is a polyvinyl toluene-based plastic scintillator, and a CCD camera have been used to image the object. Exposure times ranging from 15 minutes to 1 hour were used to image the steel tank section seen here. As there is no hydrogen in the tank, wax was filled in the defect and used as a contrasting agent to mimic hydrogen. Cadmium strip was placed outside the scintillator to be used as a reference since it has the highest neutron absorption coefficient and can be seen on the radiograph. This is the radiograph of the setup at an exposure time of 32 minutes. Faint contrast from cadmium is visible. After conducting different types of experiments by using different materials for contrast, long exposure times, a zinc sulfide scintillator, it was evident that fast neutron radiography was not going to be able to image the hydrogen tanks. The most important factor was the inadequate neutron flux produced by this generator. What is thermal neutron radiography? High energy neutrons with energies peaking from 0.85 MeV to 14 MeV can be slowed down to energies in the range of 0.025 eV to 10 kV by using a moderator material. The moderator materials are chosen such that they have a low neutron absorption cross-section and a high scattering cross-section. Water, polyethylene, graphite are often used as moderators to slow neutrons. The table here shows the difference in the scattering and absorption cross-section for iron and hydrogen at thermal energies as compared to the cross-sections at 14 MeV. It is the difference in cross-sections at these different energies which provides the basis for conducting thermal neutron radiography experiments. Thermal neutron radiography experiments were conducted using an accelerator-based neutron source at the Rutherford Laboratory in the UK. A 50 by 50 by 7 mm steel sample was imaged using thermal neutrons from a Rotax beamline that generates an approximate neutron flux of 2 × 10⁶ neutrons per centimeter square per second. The experiments were conducted in the white beam with energies ranging from 3.6 mV to 130 eV. The radiographs for the sample with and without wax clearly shows that hydrogen contrast can be imaged at thermal energies. Armed with this information, TWI conducted simple Monte Carlo simulations and planned experiments to thermalize the neutrons using a portable and continuous DT generator. A hierarchy chart shows the different approaches undertaken to conduct thermal neutron radiography using a continuous DT generator. Water was used as a moderator in the experiments conducted at NSD Gradel in Luxembourg. Polyethylene was used as a moderator to conduct experiments at the National Nuclear Research Center in Poland. 2 imaging techniques were used for each experiment. This thermal neutron imaging setup comprises of a continuous DT generator with water as a moderator. a lithium fluoride zinc sulfide thermal scintillator, and a CCD camera for imaging. Image on the right shows a DT tube that generates a neutron intensity of 10 raised to 8 neutrons per second, which is higher than 10 raised to 6 neutrons per second generated by the pulsed neutron source at Sheffield. Experiments with exposure times longer than 15 minutes were not possible due to inadequate cooling within the facility, which disturbed the camera cooling temperature and hence the performance. The experiments were unsuccessful in imaging the defects on the tanks using the CCD setup, and therefore the results are not discussed here. An alternative imaging method comprising of a metallic converter screen that converts neutrons to gamma rays and an X-ray film as a recording medium was used instead of the CCD setup. Gadolinium has an enormous resonance at thermal neutron energies, which results in a spectrum of high-energy gamma rays along with conversion electrons, which emulsifies the X-ray film. A schematic for this setup shows the back-screen imaging technique whereby the scintillator is placed behind the X-ray film. The 2 mm defect from the composite tanks can be seen on the film radiograph and is placed next to the zoomed photograph of the defect for clarity. In conclusion, the thermal neutron radiography setup using a continuous DT generator was considered partially successful and attributed to the gadolinium X-ray film setup, which imaged the defect in the composite tank. A thermal neutron radiography setup using a polyethylene moderator is shown here. The DT tube and the sample are surrounded by polyethylene blocks. The CCD detection system is surrounded by borated polyethylene to cut out the scattered neutrons. These experiments were conducted at the National Nuclear Research Center in Poland. Experiments with exposure times ranging from 30 minutes to 2 hours were conducted. This slide shows the imaging setup for a composite tank as imaged by the CCD camera. The radiograph shows the cadmium strip, which was used as a reference next to the defect but not the defect. This is a schematic to show the side view of the imaging setup using gadolinium and X-ray films to image the defects in a composite tank. The gadolinium and X-ray film combination as placed on the 1 and 2 mm defects for the experiment is shown on the left of this image, and the right is a radiograph obtained after 2 hours exposure time. An experiment was also conducted on a 50 by 50 by 7 mm sample cut from the steel tank. 2 mm diameter see-through holes were drilled in the sample. The gray circle in the schematic is where a 2 mm hole was drilled such that it did not penetrate the full thickness of the sample and was filled with borated grease. CCD imaging and the gadolinium X-ray film imaging techniques were used to image the sample. The radiograph from the CCD imaging setup is able to image the 2 mm see-through holes but not the hole in the center. The film radiograph obtained using the gadolinium X-ray film combination shows the see-through holes at a resolution of 2 mm, but the contrast for borated grease is not visible. The main conclusion from all the experiments is that the CCD imaging technique has been unsuccessful in imaging the defects, but the gadolinium X-ray film imaging technique has been successful in imaging the defects in a composite tank. None of the imaging techniques have been successful in imaging the defects in a steel tank. Overall conclusion. 3 different approaches have been used to conduct neutron radiography experiments which were presented here. The conclusions are the following. Fast neutron radiography approach based on the Monte Carlo n-particle simulations was unsuccessful. It is mainly attributed to the low neutron intensity generated by the pulsed neutron generator at the University of Sheffield. Thermal neutron radiography conducted using an accelerator-based source at the Rutherford lab demonstrated that thermal energies in the range 1 millielectron volt to 1 electron volt can image the defects created in the steel samples at a resolution of 0.5 millimeters. Thermal neutron radiography using a continuous portable DT generator using water and polyethylene as a moderator were partially successful. The CCD imaging setup was unsuccessful in imaging the defect. However, the alternative imaging technique using gadolinium and X-ray film combination was successful in imaging the defects inside a composite tank. Thank you for listening. Special reference should be given to the other SafeHPower partners involved in the project, including TWI, Brunel University, Flowtex, Accent Pro, Ceratec, Pure Energy Centre and Initech UK. The SafeHPower Consortium would like to express their thanks to Dr. John Macmillan, Dr. Winfried Kockelman, Mr. John Swed and Dr. Michał Gierlek for allowing us access to their neutron facilities and their support throughout the project. Should you have any questions, please do not hesitate to contact us. Thank you for your attention.